This is part 2 of graphing experimental data. In this video we're going to determine the slope of the graph. This is the graph of the data that we plotted in the last video. And if you're wondering about how we chose the scale and all the different parts of the graph, try to get a look at that video. Anyway, here's the part where we get the slope of this. Now, I mentioned in the last lesson that this point here is the average data point, and the best fit straight line that you could determine statistically would go through that point there. And so the way I usually do these is that I take a transparent ruler, force it to go through that point right there, and then rotate the ruler until it seems to match up with the data points best. Now, this ruler doesn't happen to be quite long enough. I want my line to go axis to axis. That's a key point, and so I'm going to use a different ruler, one that's longer. This one doesn't happen to be transparent, but it'll let me do that. And I want to make my line as long as possible, and I'm using a pencil here to make the line. The Sharpie makes such a wide line that I wouldn't be able to do it very well. So there's my best fit straight line, at least eyeballing it. If it doesn't happen to be absolutely perfect, I'm not too terribly concerned here, but I'm still going to determine the slope of this. Eyeballing a straight line, we just do the best that we can. The points that I want to use for getting the slope of the graph are as far apart as possible. Notice my line barely goes through any data points. I'm not going to use those to get the slope. I figure my best fit straight line is better than any of the data points, and so I'll use this point right here to get the slope, and then this point up here to get the slope. Up here at the top, I don't happen to have the values on the axis particularly visible. It'll help me to know that this top up here is 4.0, and the next major division down there right underneath it is 3.75. That'll help. And then on this axis, this major division here actually represents 0.95, and the units on that are meters, by the way. And this one represents 1.00, this major division. So it'll help in determining the slope to figure those things out. Now, for a little bit of review, slope is equal to rise over run. Notice that up until this point, I haven't even used the words x-axis and y-axis. That's because we don't have them here. In science, I don't know if we ever graph anything on a y-axis or anything on an x-axis. Maybe once in a while in the study of motion we might do that, have an x versus t curve, but we don't have y and x axes here. What we have is a t squared axis, that's the vertical axis, and an L axis, that's the horizontal axis. So thinking of it as rise over run is a better way to go. The rise ends up being the difference in vertical axis values. So rise ends up being how far is it from here to here, but only on the vertical axis. That's what the rise is. The run ends up being the difference in horizontal axis values. Well, on our graph, that will be how far is it from here over to here, just measured along the horizontal axis. That's how we calculate the slope. So let's try to do that here. Now, it'll help here to write this point as an ordered pair and this point down here as an ordered pair. I'll write my horizontal axis values first. Well, this one happens to be at 1.0 meters. In fact, I can do better than that. I can easily get a tenth, but since it's crossing the axis here, I can actually write that as 1.00 meters. Now, what about the vertical value here? I've got 3.75 is this major division, 4.0 is this major division. The line actually seems to be crossing right at this minor axis or minor tick mark crossing here, That would actually be 3.95. And I can read my graph that well to figure that out. So that would be 3.95. Now my vertical axis values are seconds squared. And so that's the ordered pair up here. When I do the same thing down here, this time I'll have to do a little bit of work to figure out the horizontal axis value. But this is 0.10 here, 0.20 here. Each one of these, this would be 0.11. This is 0.12, but it's a little bit to the right of that. I would estimate that that's about 0.122 meters is what that one is. 0.122 meters. Actually, I could put another significant figure on here if I want. This is actually exactly 1.000 meters. All right, now what about the time squared on this axis? Well, it's crossing this major division here. At that point, it's 0.250 seconds squared. Whoops, didn't want the parentheses yet. 0.250 seconds squared. Okay, let's do the subtraction here. Rise over run, the difference in the vertical axis values. These are my vertical axis values. I would have 3.95 seconds squared minus 0.250 seconds squared. I think I can do that subtraction in my head, but we'll be careful anyway. Difference in the horizontal axis values, 1.000 meters. It was exactly that, so keeping three significant figures after the decimal point is okay here. And then minus 0.122 meters. Notice I've written these numbers down with as much precision as I can get by reading off the graph. I didn't just write that as 1. I wrote it as 1.000. I didn't just write that as 0.25. I wrote it as 0.250. Also, I've got units with every one of these numbers on here. Good practice. Do that. Okay, do the subtraction here. I would actually get 3.70 seconds squared on top. Down here on the bottom, I'll have to pull out a calculator for that. I would get 0.878 meters. Okay, I've got three significant figures on the top, three significant figures on the bottom. I think I'll be able to keep three significant figures in my result. My slope will be 4.21. It'll have units of seconds squared per meter. Don't be too bothered by the weird units. That's just what comes out in this. That's the way you get the slope of a graph. Notice it's got units of what's on the vertical axis, seconds squared, divided by what's on the horizontal axis, meters, seconds squared per meter. Rise over run. That's the way you get the slope of a graph. Important things here, knowing the definition of the slope, that it's rise over run, or difference in vertical axis values versus difference in horizontal axis values. That's important. I made my line long enough so it was leaving the graph up here and entering the graph down here. By having that be the case, my widely separated points, I minimize error that I make in estimating exactly where that leaves the graph and where it enters the graph. That's why you make a graph so long. Other things, I kept track of units, read my decimal points very carefully, kept track of units all the way through in the calculation, and ended up with correct units, the ratio of what's on the vertical axis divided by what's on the horizontal axis unit-wise. You'll get a chance to do this in lab, and several times during the quarter we'll graph experimental data. You should have a pretty good idea how to do it, but you don't get good at it until you actually do it yourself.